Hello everyone and welcome to a video on logarithms. This video is intended for Pure Math Unit 1. In this video I'll be starting with the fundamental concept of logarithmic functions. I'll then move on to the principles of logs and then straight into past paper questions. This way you'll be able to have a real-world application and see how it's actually tested. Now with that said, let's get right in. So first what you'd like to know is that logarithmic functions are typically written in this form. We have x is equal to log, and we'll just put a number here. I'll explain to you what it means, of something here. So what these things are, x, right here, in this case, in every case, it will be the index. A is the base, and y is the number. Now, you might be saying you don't know what that means, right? And that's fine. This is just the form of logarithmic functions. This is really what you need to know. So, here's the thing now. If we'd ever like to convert through different forms, right? What we know is that if we take the base and raise it to the index, we'll get the number. In this way, we'll say that y, which is a number, is equal to the base, which is a, to the power of x, which is the index. So remember, if you're trying to convert something to logarithmic form, the base raised to the index gives you the number, right? Now, I understand that this might be a little bit arbitrary, so I'll give you, not arbitrary, sorry. I meant abstract. So sorry, wrong use of diction. Okay, so what we need to do now is to try an example. Let's say that we have a to the power of 3, and that equals 8. And we want to put this in logarithmic form. So what did I just say? I said that when you take a base and raise it to an index, it gives us the number. Now, we need to look for something that's being raised to something, and then we'll instantly know what the base is. So, a to the power of 3, that automatically means that a is the base, right? Because when we take the base raised to the index, we get the number. So we'll say log base a and index. So a raised to 3 equals the number. And we know that in this logarithmic form, we have the number right in this slot here. So it'll be log base a of 8 is equal to the index, which is 3. If that was a little bit weird and you'd like to see another example, here is one. I'd recommend that you try these examples on your own, by the way, before the video actually starts. This way you actually challenge yourself and understand it more. Now let's use numbers that should be a little bit easier for you to get. Let's say y is equal to 2 to the power of 4. So we know that a base raised to the index gives us the number, right? So we look for what's being raised to something, and we know that's the base. So log base 2 equals, we know that the index is what is equated to, so we know that it's equal to 4, right? As you see from this form up here, the index is x in this case, but now we have it as 4, just right there. And then we know that the number should be right above the base, and in this case the number is y. So a base, which is 2, to the index, which is 4, will equal y. And so we know that y will be equal to 16, but that's not the point. I just hope you understand how we get to this. Okay, now let's get into something a little bit different. This is the properties of logs. Okay, So, very important things you need to know are, first, we'll start with this. Log base A of A will equal to 1. Do you understand? Very simple. So if you have log base 5 of 5, it will be equal to 1. Log base 2 of 2 equals to 1, right? Very, very, very simple. Hopefully you get y if you convert its form, right? Let's convert it into a form that we know. A raised to the index will give us a number. So if we take A to the index, which is 1, what will we get? Well, we'll have A. And A raised to 1 is the same as A. So that's the first one. The second one is log base A of 1 is equal to 0. Let's convert it again. And the base raised to the exponent is equal to the number. So A raised to 0 is equal to what? Well, we know that any number raised to the power of 0 is equal to 1. So it's equal to 1. These are very nice little ways knowing how to prove these things. Hope you're understanding so far. Now we go on to something a little bit different. So let's say that we have log base A of x times y. This will be equal to log base A of x plus log base A of y, right? So when you see they're being multiplied, that just means that you can add the two logs separately, right? With the same base, it should be very understandable. Next, naturally, when you think of multiplication, another similar process, well, not similar, but a process that you think of because you learn them in the same time span, is division. So if we have log base A of x over y, this will be equal to log base A of x minus log base A of y, right? So we know that. Should be very good so far. Well, very good, I hope at least. Now, our next one is if we have log base A of x is equal to log base A of y, this means that x is equal to y. This is when the bases are the same, then these two numbers have to be the same, or else it wouldn't make sense. Next, let's move on. Next one is if we have log base A of, let's say, x to the n, it's equal to, okay, so let's write it so now. If we have log base A of x to the n is equal to n log base A of x. Now, why is this, you ask? Because this is kind of odd, right? What this means is that when you have an exponent here, you can move it to the front. So I'll just take this exponent here. This n, you can move it to the front of the equation or the expression. And this works perfectly fine. So let's say we had log base x of 4 squared. This would be equal to 2 log base x of 4. We just brought the 2 and put it in front. And we're allowed to do that with logs, right? Very fun little thing. Now, let's say we have log base e of e. Now, this is different, right? Log base e of e will be equal to 1. We know this from the first rule, right? The very first rule, we said log base e of a is equal to 1. But log base e of e itself can be written as ln. So we say ln instead of log base e of e. Some people say ln. I say ln because I just like it that way. But yeah, which is perfectly fine. So, knowing that ln is equal to log base e of e, we can also use ln in interchangeably with the properties of logarithms, assuming that they do apply, right? Next, let's continue. So if we have log, oh, log base a of a to the f of x, this is equal to f of x log a, or it's just equal to f of x. Because remember, we can bring this f of x and put it in front. But when we do that, we have log base a of a times f of x. But log base a of a is equal to 1, so it's just f of x, right? So, nice. Now, let's think. If we have the natural, well, so ln, I'm not sure if I stated this earlier, I can't remember if I did, but ln is called a natural log. I know I said it really close to the start, but I need to just say it again. Ln is a natural log. Why it's called that, I believe because ln has a value of 2.718, and it goes on forever or whatever. But because and because in life, lots of times we see this kind of 2.718 from this formula that's given to find ln, and so we call it the natural log because it happens a lot in nature, right? Or at least that's what I believe. I hope I'm not spewing nonsense right now. I saw it on some source. But anyways, I digress. Let's now continue. So hopefully you understand these properties so far. Very, very simple properties. I think these are all we need right now for the past paper questions, because I'll be honest with you, they're very, very simple. So I'm going to start with a very easy one. Okay, let's see. This is from June 2021, and it's number 1D. Okay, I also will be linking a pure math logs indices test document where I compiled all the tests, all the logarithmic questions from past papers from any year. I put them all into one document so that I could revise for my own tests. So let's go. Let's say you have to solve the equation log base 2 of x plus log base 4 of x plus log base 16 of x, and we say that's equal to 7. Now, first of all, what do you realize? First thing you should realize is we're using plus. Now, what did I say earlier about plus? That means that we can multiply them all. Isn't that correct? But we can only multiply them when the bases are the same. Now, how do we change bases? Very good question. This is how we change bases. We change bases by having log of the new base, so we'll call that b, of the top number, so we'll say this is a, over log of the new base of the bottom number, which we'll call c, right? This is top number, this is the bottom number. Top number meaning when you say log base 2 of whatever you say next. So for example, we have log base 2 of x would be the top number, and log base 2 of c would be the bottom number, which would be log base 2 of 2, which is 1. But we're not changing the base. So what you need to do when changing bases is always try to change base to the easiest one. So right now we see log base 2 of x, and this seems very simple. So let's convert log base 4 of x and log base 16 of x to log base 2. So log base 4 of x is equal to log base 2. So we know we want log base 2. Let's just say we know we want log base 2, but we might not know what comes after. So log base 2 of what? So log base 2 of the number at the top, which is x, over log base 2, the number of at the bottom, which is 4, right? In keeping with these rules I just showed, see a, where a is the top number and b is the bottom number, or the base, right? So let's try to convert the next one now. So we need to convert log base 16 of x into base 2. So log base 16 of x is equal to log base 2 of something let's say we don't know it, over log base 2. So again, when we're changing bases, top number goes on top, bottom number goes on bottom. And then we'll know that this is equal to log base 2 of x over, and if you plug this into your calculator, you'll see, or I don't know if you want to do that, but if you look it up, that's also easy. You'll see that log base 2 of 16 is actually equal to 4, and log base 2 of 4 is equal to log base 2 of x over 2. So now that we have everything in log base 2, right? We have these in log base 2. We can completely rewrite our original equation. Let me go up so that we can use some more space. Oh, it's such a lean line. And by the way, I haven't posted a video in a while, but as you can see, the setup is slightly different. So I'll now be using an iPad to be doing these videos, which I think looks a little bit cleaner. So yeah, so let's get back to the equation. So we have log base 2 of x plus, and we just worked it out to be log base 2 of x over 2 plus log base 2 of x over 4, and this will be equal to 7. Please don't forget the 7. So what can we do now? Now, here's a very easy way to do this. We can multiply. I want you to think about it for a second. How could we get rid of these fractions? This is very simple math, third form, very easy. What can you do to get rid of the fraction? Now, of course, is to multiply both sides by a certain number. What will that number be now? I want you to think about it, because if you're not thinking while watching this video, you'll probably not learn. So we can multiply both sides by 4. You see, because 4 will remove the denominator, right? So in this case, right, we'll end up with 4. 4 times log base 2 of x is equal to 4 log base 2 of x. 4 times log base 2 of x over 2. If you have a 4 right here and it's being multiplied, this cancel, so you have 2 left here, right? So it'll be plus 2 log base 2 of x plus 4 into 4 goes 1 to be log base 2 of x. That will just be normal. Don't forget to do your 7. 7 has to be multiplied by 4 as well, and we know 7 times 4 is 28. Right, good. Now that we have everything in this familiar form, what was one of those rules I just explained? Right? I hope you weren't lost by the change of base formulas. If you were, I'm very sorry. If anything, you can watch a video on it and come back. I just think that's a very simple formula when you do questions with it, and so I didn't want to spend too much time on it, in the interest of time, of course. So remember one of the last things I said is that if we have something in front of our log or logarithmic function, we can bring it from the power to the front of the equation, right? Now, if it is already in the front of the equation, that means that can't we just bring it back? Yes, we can. So now rewriting this equation, we'll have log base 2 of x to the 4 plus log base 2 of x squared plus log base 2 of x, and that will be equal to 28. Now, at the very beginning, I said that if it is that we had the same base, we could multiply x to the 4 times x to the x squared times x, because this is one of the first properties of logs that I showed, right? I'll go back to it right now. Sorry for those who don't actually need it. This right here, log base, actually sorry, that was what we did earlier. Right here, log base a of xy is equal to log base a of x plus log base a of y. So let's continue. Now that we know that we can multiply it since it has the same base throughout, let's do just that. So we'll have log base 2 of x to the 4 plus x to the 2 plus x. But we know it's not plus, it's actually multiplying now. Because in order for us to get the plus, we multiply. If you're screaming at me through your computer, I'm very sorry. I was just kind of trying to do this. Totally didn't sit in my mind. Totally. Right? So now we know that we can add these powers, because when the same number, the same base is being multiplied, we can just add the powers. So log base 2 of 4 plus 2 is 6 plus 1 is 7, and that will be equal, oh my, I put 16, it should be 28. Right? Now, what is something that we learned a little bit earlier? At the very beginning of this video, I showed a method of how to transfer things into logarithmic form. Sorry, I'm just opening my little study jar to take out my calculator because I can see that's going to be needed. Right? So I taught you earlier how to change forms. We know that the base to the power of something will give us the number. Now the base to the power of what will give us the number? The base to the power of the exponent. And when something is in the form of a logarithmic function, it mimics this form right here, where x is equal to log base a of y, where x is the index, so the thing that's being equal to would be the index, meaning that's going to be the power. So we already know that something is to the power of 28. But what's to the power of 28? Log base 2, so the base to the index gives us the number. So 2 to 28 equals x to the 7. In this case, x is on its own, it's not to the power. People might say, oh, x is to the power, so x to the power of something equals, like, no, that's just not how this works. So, what can we do now? We can find 2 to the power of 28 and then find the 7th root of x, but that way is just kind of annoying. So, I'm going to introduce something to you right now, and it's ln, natural log. Now remember what we did earlier when we showed log base a of e for ln? Well, something you can do with ln is actually ln both sides, and you bring down the power. What I mean by that, you can take this power and bring it down in front of the expression. So if we put ln here, we can take the power and remove it and put it to the front. So we'll have 28 ln 2, and that will be equal to, now if we took 28, which is a power, and put it in front of the natural log, and the natural log of the base, what will we do for the second part? You tell me. That's right, we'll take the 7 ln x. Now we can actually find the left-hand side. We just for simplicity's sake, we can just divide by 7 so that we have ln x. So now we know ln x is equal to 28 ln 2 over 7. So take out your calculator, you can type ln 2 multiplied by 28 and divide it by 7, right? So 28 times ln 2 divided by 7. So ln x equals 2. Wait. Oh, yeah, fine. Equals 2.8. Now, what is ln? I said earlier ln was log base e of e. So, what does that mean? It means that if we say, okay, log base e, wait, hold on, I'm thinking for a second. Log base e of x is equal, log base e of e is 1, sorry, but ln is log base e is equal to 2.8. I might have to go and correct that early in the video. So if we take e using the same reverse logarithmic rule, it being able to turn to something into a logarithmic form, using the reverse of that, we can take the base to the exponent, and that will equal to the number. So say e to the 2.8 will be equal to x. So now we have something, a value for x. We've just taken a value for x out of nothing. Let me find e button here. Okay, e to the power of 2.8. Hold on. I'm having a slight, my calculator's having like a slight issue. It's not seeming to be working. So let me use something else right now. E to the power of 2.8. And this will give us x is equal to 16.4. Now, honestly, the 2.8 is actually simplified. I just did it to one decimal place. I don't know why the calculator did it like that. But the answer is x is equal to 16. You'll be marked correctly, don't worry. But I would advise that you don't simplify it. I simplified it because it was a 9-digit number, and for the sake of simplicity, it was easier to do this than do a 9-digit number, and actually, it wasn't even really intentional. It was just the calculator ended up doing that, and I apologize. But yeah, you kind of get the gist. Now, let me do another one that I know a lot of my comrades at school were having, I wouldn't say sort of an issue, but it was definitely not something that you see every day, at least. So let's go. Let's say that we have a cubed plus b cubed, oops, plus 3a squared b, and that's equal to 5ab squared. And we want to show that 3 log base a plus b over 2, we want to show that that's equal to log base a plus 2 log log of b, sorry, not base a, 2 log b. Now, they give us kind of information in the top here, but we don't need to worry about that. What we're trying to prove is that 3 log of a plus b over 2 is equal to log a plus 2 log b. So let's start with the right hand side here. Sorry, this looks like lag, but you know what I mean. Oh, sorry, I erased the wrong thing. This should be a, okay. So, if we have the number in front here, that means we can just throw it over here. By now, these things should be becoming be a little bit more intuitive to you, should be really seeing them instantly, plus log log of b squared. And what did we know earlier is that if it is that you have something being added, you can multiply them under the same log. This is equal to log of ab squared, just the b squared, okay? So what can we do here? The 3 is in front. As you know, you can take the 3, put it to the front here. So we'll have log of a plus b over 2 to the power of 3, and that'll be equal to it. So now what can we say? We know that a plus b over 2 cubed should be, and the log of that should be equal to log of ab squared. But here's something that we do know. We work out what's inside the brackets. And to kind of shortcut the method, I'm going to use what we call Pascal's triangle. You might not know Pascal's triangle because we're not technically supposed to learn this until Unit 2. I'm still in Unit 1 as well, but for some reason I ended up stumbling across it and I thought it was helpful. So, Pascal's triangle, you can expand this bracket normally, like how you'd expand, normal cubed brackets, but for the sake of time, so we'll have a cubed plus 3a squared b plus 3ab squared plus b cubed. And now that we have two things with logs, we can just drop the logs now, right? So what that means is that we can have, oh, my AirPods are dying. We can have a cubed plus 3a squared b plus 3ab squared plus b cubed is equal to ab squared. And here's something that we need to not forget is that this is over 2. I slightly forgot it. Please forgive me. But it's over 2. So, what we need to do is to cube the 2 as well. We forgot to cube the 2. The cube of 2 would be 8. My apologies. This should be over 8 when it's cubed. Okay? So now, how do we get rid of this fraction form of 8 with over 8? Well, we multiply it by 8. We multiply both sides by 8. This will give us a cubed plus 3a squared b plus 3ab squared plus b cubed, and that will be equal to 8ab squared. Now, they gave us something earlier. It was this form. I said it wasn't useful, but I lied. It's useful, but just not yet. It wasn't yet useful. And it's that. They wanted in that form a cubed plus b cubed plus 3a squared b. Now, does that look familiar? We have a cubed, right? We have it right here. Oh, we know we have b cubed, right? We have it right there. And we want 3a squared b. We have that right here, but what do we have? We have 3ab squared, but we noticed over here, up here, it was equal to 5ab squared. So what can we do to get 5 from 8? Well, we can subtract 3ab squared because we have it on this side. Minus 3ab squared minus 3ab squared. Therefore, we have a cubed plus b cubed plus 3a squared b is equal to 5ab squared. And this is the answer. It's proved, right? So we have it back into the form that the question gave us, which I think is very good. And just to continue, we will be doing another question. I'm trying to think of a question that should be quite difficult to you. I also want to say that I do all of these without an answer sheet in front of me or anything like that. I just have the questions. I don't really know I don't really use an SSG because I prefer to do it authentic so we have what I'm actually thinking. So yes, I apologize for any mistakes I make. It's just because I might be caught up in the heat of the moment. Ah, this one. This one definitely. If you don't know it, it's probably a little bit of a doozy. Where did it go? It just disappeared. Ah, here we go. Yes, I'm trying to introduce you to every type of question at least. If not every question, I might do a live stream where I do every question. I actually did every pure math past paper for preparing for my end of term exams this year. Um, Hopefully that went well. So, right, we have this question: 3 minus 4 over 9 to the power of x minus 4 over 81 to the power of x. So, what can we do here? Instantly, what you want to do, you want homogeneity. I don't know if that's what that means. Wait, no. Yeah, homogeneity. But actually, no, not homogeneity. You want things to be the same. I'm just using the prefix homo for no reason, no, because I don't know. I've been reading a lot of physics or whatever. But yes, we want everything to be the same. So if we have 4 to the power of 9x and 81 to the power of x, how could we get 81 and 4 to have the same base? Could be either 9 or 3. How could we do that? Now 81 is equal to 9 squared, right? So let's work it out with this. If 81 is equal to 9 squared, we can say that 3 minus 4 over 9 to the power of x minus 4 over 9 squared, because that's 81 to the power of x, equals 0. Now, here's the next thing. These things right here, these two powers next in the brackets and out the bracket, second, this right here and this, these two can be kind of interchangeable, if you know what I mean. But that doesn't even matter right now. What matters, well, actually it does, sorry. We can bring the 2 out here, and we can bring the x in here. Because we want to have 9 to the power of x like it's normal. We want to have that like as a normal thing, and we can bring the 9 to the power of x by doing this. So we want both things, both denominators to be the same. That's what we're trying to do right now. So we'll have 3 minus 4 over 9 to the x minus 4 over 9 to the x, and this will be squared, right? Because we still take the 2, we just interchange them, right? That's all we're doing. We're just interchanging the 2 and 4. If you don't understand that principle, then I'd recommend that you know, check your indices, surds, that topic should be very helpful if you don't understand that. And let's move on now. I'm running out of space, so I'm just going to write over here. So, oops, I took out my eraser. So now that we have this simple form, what do we want to do now? You might be wondering, what could he possibly want to do? Now, if you remember from your indices, if you take numbers to the numerator when they're the denominator and they have a positive thing, they'll have negative. So they'll have negative powers, but we don't even need to know about that. What we want to do is we want to let y be equal to 9 to the power of x. Now, why is this? We want to find a quadratic formula, not formula, we want to find a quadratic equation out of this little thing that we've been given, okay? So we want to find a quadratic formula, so quadratic equation. So we'll have 3 minus 4 over y minus 4 over y squared. Do you see? And it will be equal to 0. Now, what could we do here? Think about what we could actually do to get everything. So we can multiply by y squared. to get rid of the denominators. So I have 3y squared minus 4y minus 4 is equal to 0. Now that we have a quadratic, we can do the AC method. Two things that multiply a times c to get. So a times c is equal to 3 times 4 minus 4, which is minus 12. And it should add to get to minus 4. So what two things multiply to get to minus 12, but add to get to minus 4? Well, that would be negative 6 and positive 2. So 3y squared minus 6y plus 2y minus 4 equals 0. Then we can factor it out, 3y, y minus 2, and then plus 2y minus 2. And this will be equal to 0. So then we can have 3y plus 2y minus 2 equals 0, right? But now we could solve for y. So either since both things are equal to 0, we can just say 3y plus 2 equals 0. 3y equals minus 2 over 3 over 3, or y minus 2 equals 0, y equals 2. Now here's something else you should know about logs. You cannot have the log of a negative number. You can't have that. So when we see this, right? When we see log of a negative number, we know that we can't actually do that. Just keep in mind. So since y is equal to 9 to the x, we say since y is equal to 9 to the x, and we know that y is equal to minus 2 over 3, we can say that minus 2 over 3 is equal to 9 to the x. Now, what we want to do is bring down this x here because we're trying to solve for x. That's what we're doing right now. We're solving for x. So we'd have ln minus 2 over 3 will be equal to x ln 9. Now, we can't have negative number of a log, so this answer is disregarded. Right? This answer is disregarded. I'm not going to write it because it's kind of unnecessary. And yeah, we automatically know this answer cannot be used because we can't have a negative of a log. So now we also know that y is also equal to 2. So since y is equal to 2, we can say that 2 is equal to 9 to the x. Let me scroll up a bit so you're not as confused. So now we can use natural log. We'll say ln 2 is equal to x ln 9. Then to solve for x, we just divide both sides by ln 9. So we'll know that x is equal to ln 2 over ln 9. And this can be your answer. Unless they ask for an absolute value of x, this could be your answer. By absolute, I don't mean positive, I mean like an actual value. And in this case, it would be, my calculator just gave me 0.3, but since it's been acting up recently, let me just double check that. ln 2 over ln 9. 0.315, yes. Okay, good. Therefore, x equals 0.315. And that will be your answer. Now, this will bring us to the conclusion of this pure math video. I think I've just about introduced you to every concept in logarithms. Again, I'll be leaving stuff in the description. I'll have timestamps if you want to scroll through any part of this video and find something you didn't understand. If I did anything wrong, you could always leave it in the comments because, again, I don't use an answer sheet. And I'm still a student, so anything is possible. Please forgive my mistakes in these videos. I'm still it's kind of weird to kind of like to be talking to a screen while writing, and so sometimes I do make mistakes, and I apologize for that. But nonetheless, I hope you enjoyed this video. I hope it was somewhat useful to you, and I hope you do well in CXE, and good luck to you. I hope if you have any other issues with this topic and would like help, you can comment down below. And if you'd like to check out my other videos, feel free to do so. Goodbye.